It's official. It is Bridge Day here at Engineering Tomorrow. We are so excited to have so many schools from around the nation joining us live today. And today, you guys are in for a treat. We have the amazing Milton Davis here to lead us in our introduction. And you guys are going to be blown away by this. But I just want you to know we love student engagement. Do not hesitate to type in chat. I know Milton has some questions for you all. So please, Milton, you can take it away.
Hey, let's do this. Monica, you always set us off straight. This is so exciting today. It's Bridges Day. It's Bridges Day. We're finally here. We're gonna build some bridges. It's gonna be a lot of fun. Maybe after you all build these awesome bridges that can support the most weight while conserving some resources, right? We're gonna talk about this. Save a little money. Maybe we'll have a little bridge building competition, right, Monica? Right, Constance? Maybe we'll have a little competition as you all show off your awesome designs. Let me give you a little bit about my background. If you haven't heard this before, I have terrible dad jokes. So let me give it to you. Why am I interested in engineering? Why am I here? Well, one, I loved RC cars. Anybody love RC cars? Maybe I can get one person in the chat that loves cars. Come on. Oh, there you go, Betsy. I love RC cars. I also love TOEs. That's not feet. It's just theories of everything. This universe, space, how it all came into existence. I don't know. I just can't get enough of it. Um, but I didn't go to the greatest school. So I self-enrolled in a community college, and while I was there, I was so blessed. My mentor at college said, "Hey, Milton, you got to put this together." So, what are you going to do? Well, I mixed that love of RC cars and I mixed that love of all things space, and I have been an aerospace engineer since 2001. That shows my age. I went to Purdue. Let's boiler up, and that's out in West Lafayette, Indiana. And that is me as an intern a very long time ago. What's up, Phelps? Phelps Ace, how you doing? A very long time ago. What do I do? I am blessed and honored, absolutely honored to be a space vehicle manager for a mission called Awesome One. And the reason it is so awesome is because we're going to be fixing satellites in space, give them a little more fuel. We're going to build some structures in space, all of that great, great jazz. We're even going to build things in space like infrastructure, just like bridges, which we are talking about today. Maybe it'll be a bridge like this one day where we're out in space, we're building different structures to navigate the next satellites into space. Maybe doing some additive manufacturing on the moon, right? We would love to go to the moon, okay? So I want to give a huge, oh, thanks, Phelps. They said that already. I want to give a huge shout out to my buddy, Joanna Cotto, who's just done an outstanding job architecting this lab. And we can't do it without our interns as well, because we want this to be so fun for you all. So why are we talking about bridges today? Why are bridges so important, Texas in the house? Why are bridges important? Well, bridges provide safe passage. I mean, in the past, when we didn't have all this awesome infrastructure and we didn't have airplanes to kind of take us to different places, there were critical resources that people needed, and they couldn't get access to those resources without a bridge. And they provide safe passage as well. So let me ask this question in the chat. How many bridges do you think there are in the United States? How many bridges? Give it to me. Come on, Maria Regina High School. How many
Te-
bridges do you
Teachers, hop into that chat and put in some numbers. Oh,
text?
Constance
Okay.
has a guess.
Constance said 100. Constance, you're cheating. You probably already, Constance already knows the answer. Thomas County, how many bridges do you think? Come on, High School for Community Leadership. I see you. How many bridges, High School for Community Leadership? 3,000. Thank you, Brian. How about you, Mount St. Michael Academy? How many bridges?
Ooh,
Oh,
oh,
oh, there's
oh,
a,
I see it.
Traverse, 600. How did you all know? 617,000 bridges. What benefit do you think there is to having so many bridges in the United States? Thank you, Mount St. Michael as well. Why is that? Thank you, Betsy. Why is it a benefit? Why is it important to have a lot of bridges? What's up, Jerry? I see you out there as well. Challenge Prep Academy said approximately 600. The access. Yeah, that's really nice. Access is important. Anyone else? Why do we need so many bridges? Why is it important? Access is a great answer. Great answer. Access is great. What do you think, East Harlem? I was just in your neck of the woods a little while ago. They put 750,000. I was just in your neck of the woods like last Wednesday. Access is good. Someone said at least five. All right. All right. That's good. They do. They give us access. You got to think about this. Your ability to go to even just different stores, to partner with different communities and organizations is huge. You got to have, Constance hit the nail on the head, you got to have access. They provide us with access. And this is one of the regions, you got to look forward to this. We're going to have a really great speaker for you today, Avery Bang. And her entire career has been around helping people that have limited resources by giving them access through bridges. And this fact alone, over 1 billion people don't have safe year-round access to education, to healthcare and markets. And Bridges to Prosperity, a shout out to her company. Bridges can give us that. All right. So let's talk a little bit about bridges. They may look different and they may have different purposes, but the beauty of it is, and when you can develop your own bridge, they all are built on the same fundamentals, right? It's you want to make a bridge that can support the absolute most weight while being efficient, while not utilizing too many resources. And you do this by controlling the forces. Now we have some of the forces on this page. We have compression and we have tension, but there's also torsion. There's the twisting force, right? There's for longer structures, there's buckling. There's a buckling force you have to overcome. There's shear, the sliding force. All of these different forces are acting against this bridge, just like with you all in life. There are different forces in life that act against you. There's pressure in life that acts against you as you try to make sure that you're doing the right things and moving forward and executing the vision you have and having fun, right? Getting through school, there's a lot of pressure. Social media, there's a lot of pressure. So what this all comes down to, just like in life and with your bridges, is how you balance all the forces. Can you balance them all? Right? Torsion, twisting, shear. Can you make sure that the structure is still sound through all those forces? And we're going to show you how to do that today. And the other thing I like about bridges, this is another thing I really, really love, is that in engineering, you can be innovative. You can still be creative and artistic. Everything, I mean, yeah, you balance the forces. Yes, they provide safe passage, but look at the artistry that they've added to these bridges in creating safe path. Unbelievable. So we want to give you some tools. Let me give you a few tools for you to think about as you're creating these great bridges. Um, Here are some really, really good shapes and structures because shape matters. Shape is really, really important. So one, there are beams, right? I'm highlighting some beams that you can utilize to provide good support. And when you have a beam, it doesn't have to just be straight across. If you add arcs to a bridge, that shape is probably the strongest shape you can create. But if you're using like bottle sticks and stuff, it may be hard to create arcs, right? There's also trusses. Triangles are very, very strong. Include some triangles in your design, and that not only distributes the load, but it increases how much strength and inertia that you have to be able to support more. So I'm going to talk about arches, and we talked about trusses. There's also some cable stays and some cantilevers that you can use as well. So let me give you a little timeline. Like how did all this come about? Well, people, these bridges actually came about because trees were falling down across waterways. And people noticed, if I take advantage of this bridge, I'll have safe, or just this structure, this tree, I'll have safe passage all the way across this waterway. So they started very simple. And then people started to take advantage of, like you see on here, this Roman arch bridge shapes. What shapes that we talked about can you identify even in this structure? You definitely can see a triangle, right? Even in this structure, you can see an arc. That provides a lot of strength to the bridge. And then they realized, hey, this is a lot of material to utilize. We're not utilizing this material efficiently. Why don't we start incorporating things like concrete, and steel and utilize, still have these very strong shapes. You see the trusses, you see the triangles, you see the arc, but far less material in order to create and maintain the structure on this bridge. So the big question is, what are you going to create? And that's what you're doing today. As a recap, you're going to develop a bridge, a functioning bridge that can support absolutely the most weight. It's going to balance all the forces, compression, tension, shear, twisting, buckling, all of that. It's going to be designed using a very important tool as well, and that is the engineering design process. We're not going to leave you out there by yourself when you're lonesome. This is the ultimate tool. It's the same tool that I've used to develop spacecraft like Awesome One. It's the same tool that they used to get the rover to Mars. It's the same tool that they've used to create, outstanding medical devices that have given people an opportunity to have a better quality of life. So you start by, you don't just have at the design, which I love to do. I love to design, so I just have at it. You start by asking some questions. First, what problem am I trying to solve? What problem am I trying to solve? The problem that we're solving today is, can you support the most weight with the least amount of materials? And then what research can I do? How can I learn from other bridges that are out there? How can I learn from other structures that are out there, right? Do a little research, then you design. And if you design and you draw it out on paper, or maybe if you even do it in something like Google Sketch, whatever tool you're going to use, before you build it, you'll do this before you build it. I promise you, you're going to make a better design. You're going to have a better design on the end. And then we've given you, and you'll see this later on, after you build it, you and assemble it, we've given you enough materials where you can test it, you can fail, and then you can try it all over again before you deploy your final design. And we see this in our wrap-up session and kind of love on you for what you've done and have a little competition to see who's made the most efficient design. All right. So I got a couple other fundamentals for you. First, we talked about forces, right? And these are the things you want to balance. You probably saw this in one of your classes where, you take a spring and you pull on it, right? It has a certain amount of stiffness. That's all a bridge is. It's, all the materials and all the shape that come together, they drive how stiff the bridge is going to be. And that also drives how much force it takes to pull on it, just like your bridge. So we have force, we have stiffness, and how it responds. And then there's an equation. You're like, man, Milton, why are you throwing an equation at me? I know there's an equation that governs all this. You may not need it today, but just to understand what's involved with the stiffness of the bridge, it's the material. This material or elasticity, every design has a different elasticity. A rubber band, has a different elasticity than a brick, which is extremely stiff, right? So you take your elasticity, you take your inertia, which is your shape. The triangles have more inertia, it's just in the shape. And you take your length, and that drives how stiff something is going to be. And then you can, on the backside of that, now when you have all that information, you can calculate how much is going to deflect, how much is going to deflect. And you want to minimize this deflection. That's what you want to minimize. So the more force you have, the greater the deflection. But the way you improve upon it, the way that you reduce that deflection, how much it moves, is by its shape or by the stiffness of the material, the elasticity of the material. Those are the knobs you have to turn, right? Let me show you shape. Again, these are the shapes. Here's an example. An arc, again, very strong straight shape. An I-beam, if you could make the, an I-beam that's something that's taller materials with less material on the inside, less mass, extremely stiff shapes. You've probably seen it in ribs that you've seen designed in certain structures. So try to incorporate this as much as you can. You probably get Amazon boxes. If you cut open that Amazon box, you'll see something called corrugation, because they have triangles and arcs in the corrugation to make it strong. All right. So here are some of the materials that we've given you. To test it, we've given you a mending plate. So you'll hook up the mending plate to some hooks, but also to make the material, we've given you a bunch of different dowel rods and popsicle sticks that you can put together with some glue also, or some tape. That's part of your engineering problem. Do you want to use glue? Am I going to use tape? What are the benefits of using glue? What are some of the benefits of using tape? You got to figure that all that out as you're making your bridge. And as a recall of what we talked about first, what's the problem you're trying to solve? That's very important. Do a little bit of research before you start making your design. Create a design solution, maybe on paper. Maybe it's on paper to kind of think it out with your team. How do we want to make this bridge? Then you build it. And after you build it, don't be afraid to fail. Every innovation I've created, every patent that I have obtained, it's all come through failures. It wasn't the wins. It was things that I learned by failing over and over again. So you want to test it, and then you're going to analyze those results. And that's our challenge today. But to make it fair, right? Because we can't have, let me see one of my schools out there. It's not fair if Mount St. Michael has titanium, and then Challenge Prep Academy, we only give them plastic. Or Mount St. Michael can make a small stiff bridge, and let me get another school. CMIT has to make a long bridge. So to make it fair, we're going to give you some constraints. Here are the constraints. One, it only can be 12 inches long. Everybody's is going to be 12 inches long. All right. And then two, 3 inches wide or less. Okay. That gives us some constraints there, some boundaries by which we all can make sure this is fair. Okay. And then so the free part, the part that's allowed to bend, that is going to be 11 inches. So you got 11 inches of what they call unsupported unsupported length. And so that you're allowed to have about an inch on both sides, or maybe a half an inch on both sides that extends beyond what is supported. Okay. So I'm going to show you an example, a really, really great example from a really, really great young engineering intern that we've had here at ET on how they tested this bridge. So you're seeing they have the mending plate, zip tied at the beginning, and they put the support. And look at that, the materials. They didn't use too many materials, very clean design. The mending plate is close to the center of the design. Question for you. Did that bridge, did it break in the material? Did it break in the popsicle sticks? Or do you think it broke at the glue? Where do you think it broke? Where, I'm gonna type this in the chat, where did the bridge break? Where did it break? Thank you, Betsy. Did it break in the glue? Or do you think it broke the glue? Oh, Lakeville. That's a good answer. Who else? The sticks. That's good. The sticks. All right. The glue. Okay. Okay. Challenge Prep Academy. It broke on the sticks. All right. East Harlem. I gotta come to your neck of the wood, East Harlem. I have to come out there for sure. Great answers. If you Challenge Prep. Someone the glue. Oh, the glue. Maria said, but Maria says the sticks. Actual sticks broke. Okay, Traverse City. Let's see that one more time. You all are on it. You all, I'm going to send this video to you so you can look at it in slow motion All of you all have excellent answers. But if you put this in slow motion, you will see that it broke in the glue. It broke the glue is what broke apart, what was detached. And that's important in many ways. One for the bridge, but one for teams. When you're working on teams, even on this team that's going to develop the bridge today, you all are the team is only as strong as its weakest part. And bridges, the how you can have the strongest dowels, you can have the strongest metal in a bridge, but if the connection, the bolts or the glue or the adhesive, if the connection isn't strong, it'll break far before the material. So if I had to give you any advice, and I've done some bridge building competitions before, but if I had to give you any advice, pay attention to the interfaces. Pay attention to how it's assembled at the interfaces. That's usually where people have the challenges. Great answers, great feedback. And finally, we want you to analyze your results. We're not just going to give out prizes for really strong bridges. These bridges for prosperity are giving opportunities to people across the world with very limited resources to have access to clean water and healthcare. But we can't do it if the bridge is millions of dollars. So we want you to sum up the cost and see if you can build the most efficient bridge possible, less materials. So we want you to cost that cost. Hey, engineering it really is about reducing cost as well. So thank you all so much. I can't wait to see these outstanding bridges that you will build today. I know you're going to kill it. We're excited about having a little bit of a competition. And I'm going to hand it off to my buddy Monica to talk to you all some about next steps, what we have involved next.
All
You're
right.
very welcome, High School for Community Leadership.